Hey everyone, welcome back to chapter 10. We are on the third lesson in this chapter. We are going to continue talking about Snell's Law today and look at some examples that are a little bit more involved than what we saw last day. Some of the examples will contain double boundaries. But before we get too crazy, I'm going to go back to this analogy with the car pulling off the pavement into the mud. You may recall that last video we used this same analogy and we talked about the car. I won't move it here if that's okay. But we said, hey, if you're a car traveling on the pavement and you receive a cell phone call and you want to pull off to the side of the road, that as you're leaving the pavement, which is fast, and the right hand side of your car hits that slow mud, it's going to bend you into the slower material because that right hand side of your car hits the slow material first, so it slows down, but the left hand side keeps going nice and fast. And it actually, if you just let go of the steering wheel, it would twist you or pull you right into that mud. So we had talked about, hey, when we actually look at angles with Snell's Law, we actually don't want to talk about the boundary, we want to draw on that normal line. So we had said that there was an angle of incidence and an angle of refraction. Remember, refracting is the bending of light at a boundary. And we talked about how the light will bend towards the normal line when you're going from fast into something slow. Now, what happens in the reverse scenario? What if we go from the muddy shoulder, you finish your phone call, and you want to pull back onto the road? So let's see if we can't sort of figure out what that's going to look like. In this case, as the car pulls back onto the road, it's actually going to be the left-hand side of the car, those two tires there, that are going to hit the fast pavement before the two tires leave the slow mud. And what's going to happen then, if the left-hand side of the car speeds up but the right-hand side is going slow, is it's actually going to bend the car that way. So when you go from something slow into something fast, it bends towards the boundary line. Or maybe a better way to think about it, since we're going to have to do this with all of our Snell's Law calculations, we want to put that normal line in. Maybe we want to think about this as when you go from a slow material to a fast material. And remember, a slow material has a larger index of refraction. Just for example, we could be going from diamond, which has a big index of refraction. It slows down a whole bunch in diamond, into something fast like air, N of 1.00. So in this case, we are bending away from the normal line. The two angles that we would be interested in would be this one here between our line or our arrow and the normal line. That would be our angle of incidence. And then we'd have our angle of refraction, the bending angle. And it actually grows in this case as opposed to getting smaller. So that's how angles work when you go from slow to fast. Let's try one example before we get into a few modified examples, a few that are a little bit more involved. So let's try this one. A ray of light travels through a boundary from glass to air. Okay. So glass is slow and air is fast. So this is the reverse scenario that we had from last video. It's the new one we've been looking at sort of to start this video. It says the angle of incidence is 41 degrees. Find the angle of refraction. I don't know what that angle is going to be, but remember, when you go from something slow into something fast, the angle is going to enlarge. You're going to bend away from that normal line. So I do know, little prediction, I do know that it should be greater than 41 degrees. So let's sketch a little picture here. I always like to draw the boundary as a vertical line, and then that allows me to always put my horizontal normal line in, which I make dotted. The dotted line just makes it stand out, especially if you don't have different colors. We know that that incoming angle is 41 degrees. And we know that the angle of refraction, we know it's going to bend away from the normal line. So I've just ballparked in there, right? No measuring with protractors or anything like that. But I do know that that angle is going to be larger on the air side, on the fast side. And if we go and plug in a value right here of 41 degrees, that's our angle of incidence, then we can hit Snell's Law. So this is that equation from last day. And remember, you kind of want to just match up Snell's Law to your diagram. Maybe don't think about ones and twos necessarily, but think about the left-hand side of your diagram compared to the right-hand side of your diagram. And if you go to run the numbers in, let's put these in. Let's go with glass at 1.50. And air, we said the index of refraction is technically I think it's 0.0003, but we're going to call it just 1.00. We'll just go 2 decimal places. We'll make life easy. I will point out that when you're trying the homework that goes with this lesson, in your textbook, it actually differentiates between different kinds of glass. So I actually just went to find the table of the indexes of refraction and realized that it's actually not in the file that I have for the Chapter 9-10 textbook questions. So I will post in the All Resources folder a separate file called Indexes of Refraction. You can go there. But do know in the homework questions it talks about crown glass versus flint glass. And they have indexes of refraction close to 1.50, but not exactly 1.50. We're just going to use that value for the notes here. So knowing the indexes of refraction, knowing that angle of incidence, we can run some easy math to go and solve for theta 2 or theta r, call it whichever you like. Again, if you go and run the numbers, works out really nice with that 1.00 sine theta, because you don't even have to divide by 1. You're going to get a decimal. Don't forget you will have to second function or inverse sine that decimal to get your answer. And it looks like 79.8 degrees. That's to be expected. We know that angle is going to get a little bit larger, and in this case it did. So there is an example looking at light going from something slow to something fast. It bends away from the normal line. The reverse scenario, if you went from air into glass, if you went into something slower, you would bend towards the normal line. So what I'd like to look at is a couple of examples where we do double boundaries. So let's think about a window. Because when you stare at something through a window, you have light bouncing off of that object, traveling through the air. The light is going to bend when it hits the glass, and then it goes back into the air before it gets to your eye. So it's actually going to bend 2 different times. So let's think about this. We've got this sort of pane of glass in the middle. We've got light that's going to strike the glass. Remember, we always want to sketch in our normal line because that's where we measure angles from in order to run Snell's Law. Now, air has an index of refraction of 1 and glass is 1.5. So if you want to sketch this picture quickly, you'd have n equals 1, n equals 1. Glass is slow. We're going to go with just generic glass. Don't ask me the difference between crown glass and flint glass and generic glass, but we'll go with that. Glass is 1.5. We know that when light goes from something fast into something slow, that it's going to get pulled in. It's going to bend towards the normal line. So there's your second angle. It's going to bend towards the normal line. And then we've got kind of a second Snell's Law bending of light here. There's another boundary. So we want to sketch in a second normal line. And then we know that we're going from something slow back into something fast. So the light's going to bend away from the normal line. So there's actually a whole bunch of different angles in there. What I would like us to do is run some numbers just based off of what if I give you that very first angle, theta 1. So let's go with that. Let's say that original angle of incidence was 50 degrees. And I have a feeling that some of you might be looking at this diagram and you might actually have a prediction as to what that answer is. we'll see if you're right. I won't actually say the number yet, but I have a feeling if you have a prediction that it's probably the correct prediction. So what if angle 1 is 50 degrees? Well, we can run Snell's Law for that scenario right there. So we're going from air, index of refraction 1, times sine 50, into glass, has an index of refraction of 1.5, and we're trying to solve for theta 2. And if you divide both sides by 1.5, and then you take a second function sine, you're going to get 30.7 degrees. So that makes this angle right here 30.7 degrees. Now we've got this second boundary, a second Snell's Law calculation we're going to have to do. And hopefully you're sort of leaning on some knowledge that you learned back in chapter 3 when we were looking at pilots. Hopefully you can see here, like, hey, Heinrich, I see a Z. I remember this, alternate interior angles from the pilots. If theta 2 is equal to 30.7 degrees, then theta 3 also has to be equal to 30.7 degrees. Those two angles are exactly the same. We had called it maybe the corners or the crotches of the Z. So if we go to run another Snell's Law, we have this angle at 30.7 degrees, and now we can solve for theta 4. And if you're smart, you're going to look at these two equations and recognize that they are actually exactly the same, just backwards. 1.00 sine 50 equals 1.5 sine 30.7. 1.5 times sine 37 equals 1 times, that's got to be sine of 50 degrees. So it's kind of cool here when you go to run the numbers. It is the same angle as before. And you might be looking at that going, well, what was the point? What's kind of cool to think about is that when you look at images through glass, because the light is going to bend when it hits the glass, and then it does sort of spit back out, if you want to call it that, at the same angle as before, you'll notice the ray of light is actually displaced. So it's actually not in the correct location where we maybe would predict it to be, right? If this light didn't bend, it would have just traveled through sort of like that. So we've got this displacement of the light where the image you see is not truly where the image or the actual object is. That's the kind of crazy thing. I don't know if you've ever learned this, but when you look at the world through a pane of glass, every object that you see is not exactly where you see it. It's actually the true object has been displaced by whatever this distance is. Let's just call it x. You can see here in this picture that the displacement of the two beams of light is probably less than the thickness of the glass. So if you are somebody who is watching this right now wearing a pair of glasses, that means that when you look at the world through your glasses, you are seeing all of the objects in a slightly different position compared to where they actually are. But when I say slight, I mean less than the thickness of the lens in your glasses. And what you can do if you do wear glasses to help you see is if you hold up something like a pencil and you look at the pencil half through your glasses lens and half just through the air, not through your glasses lens, you will actually see that the pencil does like a little shift. So if this is your glasses lens, this is what your pencil looks like. There's maybe the top of the pencil, and then you'll see that the bottom of the pencil maybe looks like that. It actually looks like the pencil's sort of broken right at the edge of your lens. And that's just because the light is bending in the glass, and here it's not bending in the air. That is not a license, though. I don't know if you're thinking about this, but I'm going to go out and say it. I'm going to sort of take myself off the hook here. That means when you drive a car, everything you see is through the windshield, through that pane of glass. That is not an excuse for mowing down an old lady in a crosswalk and then saying, oh, but I didn't know where the lady actually was because the image of the lady was displaced by this value called x. Hey, let's call up my physics teacher, Mr. Heinrich, because he just taught us that in a video. I can even show you the video. Let me pull it up on my phone, officer. We're not going to do that. There is no excuse for like running over an old lady in the crosswalk. If you're that close, you were too close anyways. And same thing if you clip a car as you're pulling into a parking spot or out of a parking spot. The pane of glass that you're looking through the windshield is so thin that you unfortunately won't be able to blame it on this. Don't use my name anyways, because I'm saying I'm off the hook. No, you can't use me as a witness or an example or something like that. You were too close anyway. But it is kind of an interesting thought. Same thing if you wear contact lenses, everything is shifted. But think about how thin a contact lens is, and then it's displaced by less than the thickness of the lens. So the world is shifted slightly, but it's by such small amounts. But still kind of a cool thought. Let's go to an aquarium. This is also a double boundary question, but this time there's 3 different substances instead of only 2. So let's say that you are out here and you're looking into the aquarium seeing a fish. So the light is going to bounce off the fish, travel through the water. It's going to hit a boundary right here. The light's going to bend. It'll travel through the glass. It's going to hit another boundary and bend, and then travel through the air towards your eye. So let's try this out. Again, maybe I'll put these indexes of refraction in. They're going to disappear on you as soon as I hit page down, but that's okay. Water is 1.33. Index of refraction for glass is 150. And index of refraction for air, we're going to go with 1.00. So 3 different substances. The first bend here from water into glass, we're going from something slower than air into something that's even slower. So I'm going to call this a fast to slow boundary because the glass is slower than the water. So we sketch in that normal line. We always want to put that in. And which way does light bend? It bends when it goes into something slow towards that normal line. So I'm just going to sketch the path here, just ballpark it. I know that it's going to bend towards that normal line. Theta 2 will be smaller than theta 1. Then we're going to hit another boundary right here. So I'm going to sketch in a normal line. Oops, got it ahead of myself. Okay, let's hold off on that thought. Sorry. Let's go with, rewind the video. What if the angle of incidence is 40 degrees? So a nice, quick, easy Snells Law. 1.33 sine 40 equals 1.5 sine theta. Divide both sides by 1.5. Second function or inverse sine, the decimal that you get. You will end up with 34.74 degrees. So that is this angle right here for theta 2. 34.74 degrees. Now we can get into that second boundary. So we're going to draw ourselves a dotted line. We're going from glass, which is slow, into air, which is fast. So we know that the light's going to bend away from the normal line. The angle is going to get bigger. But do you think it's going to be 40 degrees? And I have a feeling that you are probably thinking, maybe saying out loud, the correct prediction. And that is no, it's actually not going to come out at 40 degrees because the 40 degrees is what it would be if it went water, glass, water. But now it's water, glass, air. So we're going into something that's even faster than the water, which means this thing should bend not just back to 40, but even beyond that. Should actually bend a whole bunch. That's what I'm trying to show with that little angle there. Again, just ballparking it. I don't know what it's going to be, but I would predict that the angle would be bigger than 40 because glass to air, that's quite a bit faster than the water to glass. So we have alternate interior right in here, angles 3474 means this is 3474. And we want to go ahead and solve for theta 4. So another easy Snells Law. There's the alternate interior. Those two angles are the same. So it's 1.5 sine of that answer we found, just shy of 35 degrees, equals 1.00 sine theta 4. And if you go and run those numbers, second function or inverse sine, you will get that fourth angle at 59 degrees. And we had predicted it would be bigger than the 40. So that's perfect, right? That's exactly what we were looking for. Now, I want you to look at the math in here as well. There's something kind of cool here. Check this out. I'm going to call this right here A. So 1.33 times sine 40, I'm going to call that A. And then right here, we've got 1.50 times sine 34.74. Let's call that B. Because angle 2 equals angle 3, then this right here, 1.50 sine 34.74, those two things are the same. So that's also like saying, hey, let's call it B. And that means this thing here, 1.00 times sine 59 degrees, is C. And you might be looking at this going, what is he talking about? But you've seen things like this before. If A equals B, and B is equal to C, then A is actually equal to C, because those B's in the middle are equal. So what's super slick about this question is, if I had given you that initial angle at 40 degrees and I just wanted to know this angle out here, I said, go give me the angle of refraction in air. You actually could have skipped the glass entirely. So what's super cool, I'll fit it in at the top of the page if that's okay. Kind of weird spacing, but it'll work. You could have just done this. You could have said, let's ignore the glass because those angles are the same. And we could have said 1.33, the index of refraction for water, times sine 40 equals, skip the glass entirely, let's go straight into the air. Let's pretend the glass wasn't even there, times sine theta. And if you go and you run those numbers, you will get 59 degrees out here. So in the homework questions, there may be the odd one that's a double boundary question that's just asking you for that last angle. If that's the case, you can actually use this pretty cool little shortcut where you just ignore the material in the middle. Now, if the question wants to know the angle in the glass and then also the angle in the air, then you'll have to go do two Snells Law calculations. One Snells Law calculation to figure out this angle, and then another Snell's calculation to do that one. So this lesson, it's getting kind of long. I'm actually going to make another quick video. We didn't quite finish it. If you see any homework questions about critical angle, hold off on doing those. In fact, give me a moment and I'll pick the ones out you don't have to do quite yet with this lesson from box 3. Okay, so we are on box number 3, more practice with refraction. Here's what I want you to do for homework with this video, the first one on Snells. I actually want you to change this up a little bit. Let's go page 364, numbers 1 through 12. 13 is actually kind of a crummy question. So let's say more practice with refraction for now. Do numbers 1 through 12. So this goes with the video Snell's Law. And then I'm going to make another video, which I'm going to call critical angle. So we're just going to break this up into 2 lessons because it's kind of long. Critical angle when we get to that lesson, so after the 4th video, then you can do the 16, 24, 18, 21, 23. So that's what I want you to do for the practice. So this first video, Snell's Law, do numbers 1 through 12 on page 364. And then after the critical angle video, then you're ready to do the rest of them. We're actually going to eliminate 13. Crummy question. So there's your practice. Give that a try. Hit me up on Zoom. Send me an email if you get stuck. And look for, in the All Resources folder, I will post that table of indexes of refraction because you'll need those, and I apologize that they're not in the textbook. They are in the photocopied ones I have at school. I don't know why they're not in this one. But I will post that in the All Resources folder, just titled Chapter 10, Indexes of Refraction. Have fun. playing with the law of Willebrord von Snellius.